In this video, we are going to learn Fourier series and the Fourier transform for discrete-time signals. A discrete-time periodic signal can be represented as xn with a period n, capital N is an integer. That is xn equals to xn plus n. If we write this into a represent as a time domain continuous time, t equals to nts, where t sub s is the sampling period. We can also write this as xnts equals to xnts plus capital N ts. And that's the definition of periodicity. Xn can be decomposed as a linear combination of n harmonically related exponents. So the synthesis equation can be written in this form: xn equal to a sum. Sum is over one period, k from 0 to n minus 1. Weighted sum with weight, the coefficient c sub k, and these are the exponentials. So the exponents is e to the power positive j 2 pi k n over n. Now, if we compare this with the synthesis equation of continuous time periodic signal, the exponential in that case is represented as j to the power e to the power j 2 pi k f0 t. Therefore, we know this part is equivalent to this part, and that gives us that n over capital N equal to f0t. So if we look closely to this form, we know that n is the time index. So we have 1 over n times n equal to f0t. Now, because n is a sampling index, it's an index for sampling, so we can put a ts here and put a ts over here on the denominator. Therefore, this nts is the sample time that's equivalent to this t. What we have here is 1 over nts is equivalent to the fundamental frequency f0. So looking to a picture in the frequency domain here, for the discretized synthesis, we have n from 0 all the way to n minus 1. So we have here, this is n. With this period, this frequency n will stand for the frequency in the continuous time periodic signal, that is fs, corresponding to the sampling frequency, And if we understand that, and then we can look at the entire, this relation, which we have this 1 over nts, which is 1 over n times fs. Now this part, fs is here, over n, that is my discretized frequency intervals from here to here. This interval, which is between two consecutive frequency harmonics, that is fs over n, which is here, 1 over nts. And that is exactly the fundamental frequency as we defined before. So this part is f0, as we see in the continuous time case. Therefore, we confirm that this point, or this window from 0 to n minus 1, and then this point of n corresponding to the sampling frequency fs. If I'm writing the frequency in the unit of hertz, that's how much hertz that represent here at this point of n. With this in mind, we also understand that from here to here is my periodic window. So the next window from here to 2n minus 1 will be exactly repeat the previous values. So this is indeed because we did a sampling on the time domain. The time domain is sampled with a sampling frequency 1 over ts. So in the frequency domain, I will have copies of the signal around 0 and fs, 2fs, and so on and so forth. So this aligns with our understanding of digitization of the signal. The analysis equation is to calculate the weight C sub k. That is similar to the analysis equation we had before for the continuous time case. So C sub k equal to 1 over n, where n is the period. Summation, n from 0 to n minus 1. Because now we are dealing with discretized signal with a discretized time index n, therefore we are using summation instead of integration over t. So it's a summation within one period, n from 0 to n minus 1, xt times this call, and we are using, compared with that, we are using e to the power negative j 2 pi n k n over n. So this is the analysis equation. The Fourier series coefficient C sub k is periodic sequence with a fundamental period n. When extended outside the range of 0 to n minus 1, we know that it repeats itself. So in the frequency we already said, so all these frequency from 0 to n minus 1, all these ck's, c0s to cn minus 1, they will repeat from n to 2n minus 1. To prove that mathematically, if we are writing a coefficient c sub k plus n, we using the analysis equation, everything is the same except we plug in here is k plus n instead of k. Therefore, n divided by n cancelled out. We have another term, is this term actually times e to the negative j 2 pi n, capital N cancelled out. Now this is a 2 pi multiplied by an integer, therefore this term becomes 1, it can be removed. And this term, this expression is C sub k. Therefore we know ck is periodic with a period of n. The spectrum of xn is periodic sequence with a period of n. When xn is a real signal, it can be decomposed as a linear combination of real cosine functions, cosine and sines. So the synthetic equation can be written as this form: xn equals to a weighted sum of cosine, weighted sum of sine, with all these coefficients a0, a sub k's, k from 1 to l, b sub k's, k from 1 to l, can be related with coefficient of c sub k in this format. Well, again, because cosine is an even function, sine is odd function, so I only need to write out on one direction from 1 to k, k from 1 to k. Similarly, we can discuss the power density spectrum of periodic signal, and the signal is discretized. So the average power of discrete time periodic signal with period n, it is the energy of the signal over one period divided by the span of the period. And therefore, after some calculations, we find out it is equal to the sum over one period of c sub k absolute value square. Therefore, c sub k absolute value square is indeed the power spectrum of the signal. The energy of one signal period is we have the instantaneous power sum over one period, n from 0 to n minus 1. This can also be written as we sum over the power spectrum c sub k absolute value square over one period. Now this period is the frequency period. It is also indexed from 0 to n minus 1. Well, we need to multiply by n, make it equal to the energy over a single period. If xn is real, due to the equation, the analysis equation, we can find out c sub k is conjugate symmetry. So c sub k conjugate equal to c sub negative k. Equivalently, the amplitude of C sub k is even symmetric, and the phase of C sub k is all symmetric. With similar discussion as continuous time aperiodic signal, we can find the Fourier transform of discrete time aperiodic signal. Here, I am still have this discrete time signal. However, the period of the signal and it's become infinite. The analysis equation, which is the direct Fourier transform, we write this first. So it becomes that. This is a well-known Fourier transform for discrete time signals. So the time domain signal is xn multiplied by this core, which is e to the power negative j omega n, and sum all these together over the discrete time index n. And then we have a frequency domain signal, capital X omega. Because we are discretized in time domain, we know in frequency domain it's periodic. Therefore, we only need to express this X omega in one period, which is 2 pi. A period is 2 pi. So we can either express omega in an interval from negative pi to pi, or from an interval from 0 to 2 pi. As long as the period is 2 pi, I include all the information. The synthesis equation is the inverse Fourier transform. So if I have this frequency domain signal, capital X omega, I want to find the time domain signal xn. What I can do is do 1 over 2 pi integration negative pi to pi x omega times the core, which is e to the power positive j omega n d omega. Okay. Now we need to notice that, we need to understand that because x omega is a continuous variable. It is continuous variable, but it's x omega is periodic. So we do an integration over one period of 2 pi. So you can starting from negative pi to pi or from 0 to 2 pi. And then this integration will be divided by this period. Period is 2 pi. And then we get the time domain signal xn. So this is the inverse Fourier transform for discrete time signal. Now, why do we have a continuous variable in the frequency domain? We change that to a continuous variable in the frequency domain where omega is a continuous frequency. The reason is that we are dealing with an aperiodic signal in the time domain. So xn is aperiodic signal. And we know there is a duality. If I have a periodicity in one domain, that will give me the discretization in the other domain. So if in time domain it's aperiodic, in the frequency domain, I don't have discretization. It's a continuous variable. On the other hand, now I have discretized in time domain. Therefore, in the frequency domain, that should show me the periodicity. So the period is indeed periodic. The x function as a function of frequency is indeed periodic with a period of 2 pi. Mathematically, to show that, so if I have a frequency domain signal x omega plus 2 pi k, we plug in using the analysis equation. So we change this omega to omega plus 2 pi k. And similarly, we find out because this term of e to the negative j 2 pi kn, this is an integer multiplication of 2 pi. Therefore, this term becomes 1 and it will be removed. And what's left is xn times e to the power negative j omega n. And this is the synthesis, this is the analysis equation that will give me x omega. Therefore, capital X is indeed a periodic function with a period of 2 pi k. So this aligns with what we discussed before. If I have a frequency domain picture here, this is my 0, and I have 2 pi here, 4 pi here. So let's say I got a x omega look like this. This is x omega. Let me just show in the absolute value so I can draw on this 2D picture. I should have another copy centered at 2 pi, another copy centered at 4 pi, another copy at 6 pi, another copy at negative 2 pi. This is due to the fact that are discretized in the time domain. And what do you think about this frequency point at 2 pi? What does that stand for? Well, that stands for the sampling frequency, which is Fs, which is 1 over T sub p. So if we get all these together with previously, we know when we're dealing with a discrete-time periodic signal, this point is capital N. Now here is discrete-time aperiodic signal. This point is 2 pi. Therefore, we have a period from 0 to 2 pi. And at this point in frequency, it all corresponding to the sampling frequency of Fs. Because Fourier transform is an infinite sum, we need to discuss the convergence of the Fourier transform. Define a finite sum, x sub n, where the summation takes n from negative capital N to capital N. So we have a finite sum. Uniform convergence is defined as if I compare my Fourier transform x omega to this x sub n omega, which is the finite sum. It's a supreme over all omega. Then take the limit of n approaching infinity. If the difference between these two and the supreme of the difference between these two over all frequency is 0, then this Fourier transform converges. Unit convergence is guaranteed if the signal is absolutely summable. So we have this, and then we can find a convergent Fourier transform result. There is also another definition of mean square convergence. Mean square convergence compare the Fourier transform result and this finite sum. If the absolute value square can integrate over one period, negative pi to pi of the omega, if n approaching infinite, this mean square error mean square difference between two is 0 for all frequency omega, then we call this Fourier transform converges. Mean square convergence is for finite energy signals. So the condition is that the signal xn absolute value square summed together, which is the energy of the signal, is finite. To look at the energy of discrete-time signal xn, and we can derive the possible relations for the discrete-time aperiodic signal. So the energy is defined as the sum n from negative infinity to infinity of all these instantaneous power. And that can be written in this format, and we know using the analysis equation or the inverse Fourier transform, we expand one of the xn in this format. Then we change the operation of integration and summation. So we change the order. Summation bring to the inner part sum over index n, and it's from negative infinity to infinity xn e to the power negative j omega n, because we have index n here. And this part is our Fourier transform that give us capital X omega. Therefore, the entire thing, it will give me 1 over 2 pi, which is 1 over the period, integration over one period, negative pi to pi, x omega, absolute value squared d omega. Therefore, the x omega absolute value square can be defined as the energy density spectrum as we did before. If xn is a real signal, then x omega is conjugate symmetry. That means the amplitude of x omega is even symmetry, and the phase of x omega is odd symmetry. It follows that the energy density spectrum is also even symmetry. So we have here on the frequency domain omega, if I draw the spectrum, energy density spectrum, it should be even symmetric around omega equal to 0. Recall the Z-transform that we learned before. Z-transform can be written in this equation. So Z-transform is also a summation of xz times this power term instead of an exponential. So it's an infinite sum, n from negative infinity to infinity. We take the discretized input signal, the discrete time domain signal xn, times the power term. Don't forget, for Z-transform, we also need to define the region of convergence, where z, the absolute value of z, is between two radians, R2 and R1. If we are writing the complex number z in its polar form, so it can be written as the mode or the amplitude r times e to the power j omega, where omega is the phase. We plug into our Z-transform sum of this definition sum. So we have this part z to the power negative n becomes that. Okay. So we group xn with r to the power negative n. We find out this is very similar. This is the core of my Fourier transform. So the entire sum looks very similar to the Fourier transform. So if xz converges for z equal to 1, which means the unit circle is within the region of convergence. So it makes sense for me to discuss on the region of convergence. Now, the region of convergence, the unit circle z is equal to e to the power j omega, with r being 1. Right? Because it's in the region of convergence, so it makes sense we can discuss on this term. So we evaluate my Z-transform capital XZ, is the signal in the Z domain. Evaluate on the unit circle where z equal to e to the power j omega. So that is equivalent as x omega, which is the Fourier transform, xn, the discrete time signal xn, times this core, this exponential e to the power negative j omega n. We write out this relationship of Fourier transform to the Z-transform again here. It can be seen that the Fourier transform is a special case Z-transform. It is a special case of Z-transform that evaluated on the unit circle. So if you think that Z-transform is we have a signal as a function of z, where here is a real part, imaginary part, on the z-plane. And then the Fourier transform is just we evaluate everything on the unit circle. So we're taking this route from here, where omega is starting from 0, go all the way to pi over 2, pi, 3 pi over 2, and back to 2 pi. Okay, so here is the omega. If xz does not converge in the region z equal to 1, the Fourier transform does not exist. So we need to make sure when we're talking about Z-transform, there's an issue of region of convergence. So if this unit circle is in the region of convergence, therefore the Fourier transform exists, then we can talk about this relationship. So we see that it's a very special case. I'm not going to take all these complex z values. I'm only going to take the value on the unit circle. That gives me the Fourier transform value of x of omega, where omega in one period is from 0 to 2 pi, okay, or from negative pi to pi, and anyhow the period is 2 pi. Now we see exactly from this picture, because it's a special case of Z-transform, and we are travel along the unit circle. Of course, when we circle back and across 2 pi and cross over, and that will give me an ambiguity of 2 pi times k. And that's exactly what we have here. That's the period of 2 pi. If you go beyond that, it will repeat itself in x omega. So remember this correspondence. This is the bridge between Z transform and the Fourier transform, where Z is equal to e to the power j omega, meaning that I'm only going to look at a particular case that's evaluated on the unit circle of the Z plane. That will give me the Fourier transform x as a function of this omega. Instead of general form, x is a function of this complex number Z. Finally, let's look at the frequency domain classification of signals. And we introduce the concept of bandwidth. Because we have density spectrum, whether it's power density spectrum or energy density spectrum, whether your signal is periodic or aperiodic. And then we can use this to examine if my signal has a concentration of energy at the low frequency portion or high frequency portion or bandpass, which is within a certain frequency range. So we have a low frequency signal where the energy is concentrated at around DC from 0. And then here on the right, this is the picture of a discretized signal. So x omega, we know after this 2 pi, it's periodic, it's a copy. So we are only looking at one period from negative pi to pi. Pi being the highest frequency that I can have in this discretized signal, and which is an Nyquist rate, Fs over 2. And 0 is, of course, the DC. So in this case, that is my low frequency signal. Now, for the high frequency signal is that I have a power spectrum, or the density spectrum is very small, around DC, but high, we have a high energy concentration at higher frequency. In this case of discretized signal case, x omega, is we have a high concentration around pi, or negative pi, which is the high frequency, and this is the high frequency signal. A bandpass signal, that is, I have energy concentration within two bandwidths, within two frequency f1 and f2. We have a bandwidth here, we have a band here within f1 and f2. I have a band here that has a higher signal energy concentration. So the bandwidth is a quantitative measure of this range from f1 to f2 that has a higher energy concentration, f1 to f2. The quantitative measure is usually for a continuous time signal. We said if the signal power has dropped 90%, and we call this bandwidth is 90% bandwidth of a signal, which is between f1 and f2. Then the bandwidth given by this range of f1 subtract f2. Sometimes we will also use some other definition, for example, using the 3 dB bandwidth, which means that from the peak that I will drop about a half, that's 3 dB of energy, and the bandwidth from here to here is called the 3 dB bandwidth. Okay. And this can all be designed customly as what we defined here. If the bandwidth is much smaller than the center or the media frequency of f1 and f2, we call this a narrowband signal. So visually, on a frequency domain picture, we got f1 and f2, and this is the main concentration of my signal energy. This bandwidth is much smaller compared with the frequency f1 and f2, or the media of these two, and then we call this a narrowband signal. Otherwise, if I have a signal bandwidth that is comparable to f1 and f2 frequency, and then we call this a wideband signal. A band limited signal is, on the other hand, if my signal is nullified to 0. For example, I can have a band-limited signal from DC to a transition frequency of B. If beyond this frequency, my energy concentration is almost 0, and then I call it band-limited. It's also another name calling a low-pass filter. So similarly, I have here, if I have a signal from omega 0 to pi, which is in this case the higher frequency that I have, within this range it is 0, and I have a signal coming from 0 to omega 0 that has a non-zero value of x omega. If this is the case, I also call the signal a band-limited signal. The reciprocal relationship or the reciprocal principle tells us that no signal can be time-limited and band-limited simultaneously. So if my signal is band-limited, ideally I have a signal that has dropped at frequency, let's say omega 0 to pi. Here's 0. So this is a band-limited signal. Now, if it's a real signal, then I have another negative frequency part. It's all the way to negative omega 0. Ideally, beyond omega 0, it's all zeros. So it's band-limited signal. And the time domain signal, if I'm doing a inverse Fourier transform, the time domain signal, in this case, we will give us a sinc function. So a rectangular box and a sinc function is a Fourier pair. So the sinc function looks like this. Okay. And here is my time domain signal xn. It goes forever. It's not going to be limited in time. Therefore, indeed, I have a perfect limited in band, in frequency. Then I cannot limit the signal in time. It goes beyond to infinity.